Our goal today is to sketch radical functions. If we want to sketch radical functions, the first question we might ask ourselves is, what does the most basic radical function look like? Y equals the square root of x. Well, for example, we know the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. And square root of -1 or -2 or -3, these are all imaginary numbers. So that's our first hint. 0 is the first number we're allowed to substitute into the function, and we get a real y value out. So that's called the vertex, the starting point. And if we plot the points 1, 1, and then we go all the way over to 4, and up to 2, 5, 6, 7, 8, 9, up to 3, we can see that it's sort of slowly growing, right? It made sort of dramatic growth after the vertex, and then to get to the next y value of 4, you have to go all the way over to the x value of 16. So here's our parent radical function. If we had time to play around a little bit more, what you would notice is that this function in vertex form has the general formula a times the square root of x minus h plus k, where the vertex is at hk. H behaves counterintuitively. That is, if, for example, we have x minus 3, you would think, oh, that would be to the left. Instead, it's moving to the right. K behaves exactly as we think. And a is the leading coefficient. So if a is positive, the function will have the same shape as our parent function. If a is negative, that causes a reflection across the x-axis, so it will decrease rather than increasing. And of course, if a is really large, you're going to stretch the function out. If a is small, between 0 and 1, you'll shrink it. The same is true for the absolute value of a. If a is like -10, it causes a reflection and a stretch. If a is between 0 and -1, for example, if a is -0.8, then it causes a shrink and a reflection across the x-axis. Let's take a look at a couple examples. If we have the function f of x equals square root of x plus 16 minus 5, we know immediately it has a vertex at -16, 5. Of course, we always want to find the intercepts because those are interesting points to plot. So let's find the x-intercept first. We know that no matter what kind of function it is, you always find the x-intercept by setting the y value equal to 0. And now you guys are quite good at solving radical equations, so you isolate a root, square both sides, and then solve for x. Now these are tricky. You must always, always, always check to make sure indeed that 9 works, that it's not an extraneous solution. And that works. Good. Okay, so our x-intercept is the point 9, 0. We also want to find, I'm just boxing these in, they're not the final answer, but they're interesting points, so I want sort of easy access to them. We also want to find the y-intercept by setting x to 0. So f of 0 equals the square root of 0 plus 16 minus 5. Now, you're not going to get any extraneous solutions here because you didn't solve anything. You didn't move terms around. Rather, you just evaluated, meaning found the value of them. But if you would like to double check, by all means, be my guest. And now we're going to plot. I don't care if your sketch is, oops, I'm so sorry. Our vertex is -16, -5. This x value behaves the opposite way we would expect, but the y value of the vertex behaves the same way that we would expect. Sorry about that. So -16, -5 will be approximately here. We've got a y-intercept that's negative, and an x-intercept at +9. So I'm just going to plot these 3 points, and then I'm keeping in mind the vertex is the starting point. That's telling us this is the first x value you can put into the radical to not get a negative number in the radical or an imaginary number. So here's our final answer, the sketch. Okay, example 2. We're going to do the same thing here and start with the vertex, hopefully without any errors this time. We have the vertex will be +3, +7. Again, behaves the opposite way as you think it will, behaves the same way as you think it will. Now we'll find our x-intercept by setting y equal to 0. And then isolate isolating the root, except perhaps for a coefficient. Get that negative value in there. So we have 49 is 4 times x minus 3. So we have 49 over 4 is x minus 3. X is whatever this number is, 49 over 4 plus 3. Well, it's kind of a weird number, but that's all right. They don't always have to be integer values. Let's double check. Square root of 49 over 4 is the same thing as the square root of 49 over the square root of 4. And so this works, okay? So it might be helpful at this point to take this number, type it into your calculator to get a decimal approximation. This is 15.25, 0 is our x-intercept. Of course, if you type this in as a decimal and use the decimal form to check your answer, that would also be fine. Let's find the y-intercept now by setting x equal to 0. So g of 0 is negative 2 times the square root of 0 minus 3 plus 7. You get negative 2 root negative 3 plus 7. Now we all know that the square root of a negative number is imaginary. And we can't plot imaginary points. So we conclude that there is no y-intercept. Okay, that's no problem. Let's graph the points that we have. So we have a vertex at 3, 7. And we have an x-intercept at 15.25, 0. Well, if this is our vertex, it's our starting point. We need to start from there and go towards the x-intercept in that nice curve. See, it's a sort of a dramatic or quick curve at the beginning and then a slower curve. Let's look back at our original function and we see that the leading coefficient was negative. Oh, so it makes sense that my parent function, the shape has been reflected across the x-axis. So now it's shaped like this. Okay, here's our final answer, our sketch. All right, one more example for today. Again, same routine. Let's find the vertex. Is at 11, negative 6. Double checking my signs. The x-intercept is where y is 0, or h of x. Off to the side, maybe I'm squaring the negative 1/3. Oh yeah, that'll just give me positive 1/9. I can get rid of that 1/9 in two ways. I can multiply both sides by 9, or I could divide both sides by negative 1/9. Look at 324 is x minus 11. We add 11 to both sides. And just double check it real quick. Oops. By substituting into the original equation. You can, of course, just take this entire expression and type it into your calculator if you prefer to do it that way. But notice I'm not moving terms around to double check. I am simply evaluating, which means I'm just moving the numbers down by using PEMDAS. But 0, of course, is not equal to negative 12, and so this doesn't work. Therefore, there are no x-intercepts. Okay, we found the vertex, we found the x-intercepts, or lack thereof. Let's find the y-intercepts and then throw them in a graph. But a negative number and a square root is an imaginary number. We can't plot imaginary numbers, so there are no y-intercepts. Oh, interesting. This function only has a vertex at 11, negative 6, and then no other anchor points. So if we want to know what it looks like, we have to think really carefully about the value of the leading coefficient, this negative 1/3. We know that a radical function is typically shaped like this, but the negative sign will reflect it, and the 1/3 will shrink it. So we're going to have to make that shape using our vertex.